Hi everyone, my name is Shubhr and today I'm going to be discussing our work on domain adaptation in acoustic scene classification using prototypical networks. So acoustic scene classification is a research area that deals with correctly identifying the scene or the environment in which an audio recording was made and assign a semantic label to it. By semantic label, I mean whether it's an office, a park, an airport, metro station, just to name a few. And our work here deals with a particular domain adaptation scenario with regards to this particular research area. So what is a domain adaptation? In general machine learning terms, we have a training set, we have a test set, we train our machine learning model on a training set and we evaluate it on the test set. But in domain adaptation scenario, the training set and the test set both come from different distributions, whereas in a general scenario, they both come from the same distribution. And why do we want to explore such a problem is because it has been seen that when the data distribution changes, the performance of the machine learning model degrades. So we want to particularly explore this domain so that we ensure that our machine learning models are robust enough even if they encounter out of distribution samples. A domain mismatch in audio domain can be caused by any number of factors. It can be caused by the source domain and the target domain data set recorded in different cities or with different recording devices or under different weather conditions. All of these things can cause a domain shift in the data set. And it has been seen that supervised domain adaptation models usually outperform the unsupervised model, but they require a significant amount of label data from the target domain, which is not always available. So our idea is to explore a supervised model that can adapt to the domain shift in the audio data set with only a few examples. When I mean few, I say 5 or 10 examples per class from the target domain. And in this particular work, we are exploring a city-based domain adaptation where the source domain and the target domain data has been recorded in different cities. The model that we explored is a metric learning-based model, which is prototypical networks, which was proposed by Jack Snell in 2017. And the core idea of this model is that there exists an embedding space, sorry, there exists an embedding space where the learned representation of a particular class cluster around one single point, and which is the class prototype. And this class prototype is the average of these learned representations. The methodology follows an episode-based training where in each episode, you select a mini batch and then you divide the mini batch into a support set and a query set. The support set and the query set in this particular work have the same configuration and the same size. When we mean same configuration, what we are referring to is, let's say, we say a 10-way 5-shot classification. So what we mean by that is that our support set contains 10 classes with 5 samples in each of the class. So the support set is passed through an embedding function, which is our selected neural network, and is projected onto the embedding space where we calculate the class prototypes by taking the average of the class representations. And then the query set is passed through the same embedding function and projected onto the embedding space where for each query sample, we take a distance from all the class prototypes, and it is classified into the particular class based on the least distance from a particular class prototype. The predicted label is matched with the ground truth label of the query set, and then the error is back propagated to adjust the weights of the neural network. During inference, the same procedure is followed, excepting for adjustment of the weights of the neural network. The data set that we have used is TU Urban Acoustic 2019 development data set, and it's an urban data set with 10 classes and 1440 samples in each class. And this data set has been recorded across 10 European cities, where each of the European cities contain equal number of classes, which is 10 classes, equal number of samples in each class. So data from 8 cities forms the source domain, and the remaining 2 cities form a part of the target domain. And we experimented with different combination of cities to form the target domain, just in case to reduce any bias that is that creeps in due to selection of a particular combination of cities in the target domain. For the baseline model, we select a 4-layer CNN that was adapted from a model that was proposed by CVSSP team, in 2018 for acoustic scene classification. And the vanilla flavor of this model, we train it on the source domain data set and we evaluate it on the target domain data set using classification accuracy as the evaluation metric. Then we have different flavors of the baseline model, where baseline 50 refers to where we select 50 samples from the target domain data set and include it in the training set, and we train the baseline model again from scratch on the source domain data set and evaluate it on the remaining target domain data set, where these 50 samples are not part of the target domain data set anymore. A similar case is for 150 and 250 samples for the baseline. For the prototypical networks, we select 4 networks, where prototypical networks 10-way 5-shot is that support set in each episode contains 5 samples from each of the 10 classes, and these 5 samples are selected at random. Prototypical networks 5-way 10-shot is we randomly select 5 classes in each episode and 10 samples per class, and that forms our support set. Prototypical networks 10-way 1-shot means we select 1 sample per class, and prototypical network 0-shot means that the training procedure goes in the same way as a 10-way 5-shot, but during inference, we do not select any samples from the target domain and only use samples from the source domain to calculate the prototypes. As you can see from the results, the prototypical networks outperform all flavors of the baseline model across all the experiments, excepting one case where the baseline 250 performs better than the prototypical network 1-shot. But otherwise, we see a significant amount of increase in the classification accuracy from the baseline model across all the flavors of the prototypical networks. So to conclude, we saw that prototypical networks does outperform the baseline model in this particular scenario. However, we need to confirm this in a more thorough way. We need to explore with scenarios with different recording devices and in different kind of acoustic scene data sets to confirm that prototypical networks does outperform baseline models. And this is just for this baseline model. So we need to explore this methodology with different baseline models and select some state-of-the-art supervised domain adaptation models and compare it with prototypical networks. But all in all, this is the first step towards acoustic scene classification from our side in domain adaptation and acoustic scene classification. And we see that distance-based learning is a promising avenue in this research direction. So this was our presentation. Thank you very much for listening. And if you have any questions, I will be there. Thank you.